The limit comparison test. If the positive function f and g are continuous on the interval a to infinity, and if the limits at x go to infinity of f of x over g of x is a finite number L, then the integral from a to infinity of f of x dx and the integral from a to infinity of g of x dx both converge or both diverge. The advantage of using the theorem to determine whether the integral is convergent or divergent is that we do not need to come up with a good working inequality. Usually, coming up with an inequality can involve algebraic manipulation, which can be quite challenging. Thus, with the limits comparison test, we just simply take the limits of the ratio. If the limit is a finite number, then both of the integrals are convergent or both divergent. For example, determine the conversion of the integral from 1 to infinity of the square root of 1 plus x squared dx. Notice that we had to come up with an inequality to do this because this 1 over the square root of 1 plus x squared looks like 1 over the square root of x squared. We only use the leading terms. And this is 1 over x. And we also know that the integral from 1 to infinity of 1 over x dx is divergent because it is the p integral with p equals 1. But when we try to compare the two, we notice that this integral is below the 1 over x. That is, y equals 1 over x is above 1 over the square root of 1 plus x squared. And knowing that the larger integral is divergent doesn't mean that the smaller integral is divergent as well. Thus, we couldn't come up with a good inequalities. To avoid working with the inequality, we would just simply take the limit of the two. We set up the limits as x go to infinity of f of x over g of x. It doesn't matter which one we use f of x and which one we use for g of x. Let's just say that 1 over the square root of 1 plus x squared is f of x and 1 over x is g of x. This g of x, the integrand of the integral that we use for the comparison, we must know whether the integral is convergent or divergent right away. For example, we use 1 over x because 1 over x is 1 over the square root of x squared, which looks very similar to 1 over the square root of 1 plus x squared. At x go to infinity, these two functions behave almost the same. And we also know the integral of 1 over x dx from 1 to infinity is divergent. Now, knowing that the integral from 1 to infinity of 1 over x dx is divergent, we are hoping that this limit is a finite number. If this limit is a finite number, then by the limits comparison test, both of the integrals are divergent. We rewrite these limits as the limits at x go to infinity of 1 over the square root of 1 plus x squared times x over 1. We can just simply use the pre-calculus method to find these limits. That is, we divide by the numerator and the denominator both by x. But in the denominator, the x inside the radical is x squared. Thus, this is the limits at x go to infinity. In the numerator, x over x is 1, and in the denominator, the x in the denominator is now x squared inside the radical. Thus, inside the radical, 1 over x squared plus x squared over x squared. X squared over x squared is 1, and as x goes to infinity, 1 over x squared is 0. The denominator is now the square root of 0 plus 1, which is the square root of 1. So this limit is 1, which is a finite number. And we know that the integral from 1 to infinity of 1 over x dx is divergent. Together, the limits comparison test tells us that this integral is also divergent.